And if I now let my delta t go to 0, what happens to this term? Well, if delta t is 0, 4 times 0 is 0, and we're left with this. The velocity at t1 is equal to 8t. And so what that does is it's giving me a way to find what we call it gives me a way to find what's called the instantaneous velocity. The instantaneous velocity. So, now, to get an actual value, you'd have to plug in a time. Let's say that this is my function. If t1 was equal to 1 second, the velocity would be 8. Because if I plug in 1 second here, the velocity is 8. But it also means that if t was 2 seconds, my velocity was 16. 3 seconds, it would be 24, which actually makes sense with our conceptual framework, because if this is a parabola, I know that my velocity graph would be linear, right? This is y equals mx plus b. This would give me a linear velocity graph where the slope was 8, which I think is kind of cool. It does beg the question, though. If my original function is 4t squared, and that's for the position, and my velocity function is 8t, I wonder if there's a relationship between those two expressions. Okay? Is there a relationship between those two expressions? And frankly, I just don't know. But let's see if we can do this thing again. Okay, let's see if we can do this thing again with something a little bit simpler and see how it works out. So let's take a different function. Let's actually take a simpler function. Okay? What if my position time graph was linear? What if my position time graph is linear? Well, the thing that's interesting about this is, if this is linear, it's just not that big of a deal. We know that the slope of this line is going to be the velocity. But let's see anyway how it manifests, because I think it might be interesting in the long run. So if I think about, here's my t1. So if I want to get the velocity, I would take the slope of that. But let's use our limit again. Let's use our limit idea again and see if we can follow the same steps, and maybe the conclusion will help us generate a general idea of how these things work. So let's give this a function. Let's say the function for this is the position is equal to 3t plus 2. 3t plus 2. Okay? That would be this, okay? Because it's y equals mx plus b, so 3t plus 2. So how am I going to express the slope? Well, according to what we did before, so there's our expression, is that the slope is the limit as the delta t goes to 0 of x2 minus x1. So how am I going to express x1 and x2? Okay, how am I going to express x1 and x2? Well, so position at time 2 is equal to 3 times time 2 plus 2. Position at time 1 is 3 times time 1 plus 2. I'm going to use this same substitution here and here. So I use the same substitution, and so now I have my x2 in terms of t1 and delta t. I have my x1 in terms of t1. Let's bring them over here. And that's all over delta t. So let's distribute and see if we can simplify. So when I look at this, one of the things I'm noticing this is 3t1, this is negative 3t1. If I add those two together, they equal 0. This is plus 2, this is negative 2. If I add those together, they also equal 0. So this actually turns out to be very simple. So now we end up with the velocity is the limit as delta t goes to 0, but the only expression I'm left with is 3 delta t over delta t, and somehow those delta t's magically disappear. We call it canceling. And I'm left with the velocity is equal to and since we lost all our delta t's, if the velocity, we don't care if it goes to delta t now, so it turns out that the velocity is just equal to 3. Well, I feel like we actually kind of knew that, didn't we? Because if we come up here, our definition, if we have a position time graph, our definition is the slope of the position time graph is the velocity. So we knew that the velocity was 3, and we got 3, and that seems pretty cool. So now we're left with this idea of how exactly does this expression relate to that expression. Now, I'm going to hedge a little bit, and I'm going to write in some stuff here that may not be obvious. For example, this is here is x is equal to 3t raised to the first power. And this one is really 2t raised to the 0 power. Now, we don't normally write it that way because anything raised to the 0 power is apparently 1, although I don't really understand that anyway, but let's pretend that's true for now. So when I come over here, I'm looking at this. This is 8t to the first power. And its parent function, the position function for this one, the position was equal to 4t squared. So what are we noticing here? Well, one of the things, oh, sorry, I forgot one. This is t raised to the 0 power. One of the things that I'm noticing right away is that the position function is squared, is the second power, and the velocity function is 1 less. I don't think that's a coincidence, because when I look at it here, this is t to the first power, 1 minus 1 is t to the 0 power. I don't think that's a coincidence. I'm also noticing something else that may not be obvious, or maybe it is. This is an 8 in front of this. How does 4 relate to 8? Well, 4 times 2 is 8. If I apply that same idea here, what's 3 times 1? It's 3. So I don't think that is a coincidence at all. In fact, what I'm seeing here is the development of an algorithm that we might be able to use a cheaty shortcut method to do this thing here so we don't have to go through these 100,000 steps every time. And here's the algorithm. Let me see if I can make it easy for you. If you have a position function, which is t to some power, it could be t to the first, it could be t squared, it could be t to the third, I'm going to say t to the n. And let's say you also have some coefficient up front, which we'll call a. If I look at this as a concept, how do I find the velocity? Well, one thing I notice is that you have to definitely subtract 1 from your exponent. And it looks like, and I don't think this is a coincidence, that to get the new coefficient, you take the original coefficient and multiply by the previous exponent. So let's see if this works. What if the velocity function is the original coefficient times the original exponent, and then the new exponent is the original one minus 1. So what are the steps here? So step 1 is multiply the coefficient by the original exponent and then subtract 1 from that original exponent. So let's see if we can do that. Multiply the coefficient by the exponent, 4 times 2 is 8, and then subtract 1, 2 minus 1 is 1. Now, you did the same thing here, but I know you're asking, like, well, what about the second term? What about the second term? Let's do the first term first to make sure it works. Multiply the coefficient by the exponent, 3 times 1 is 3. And then subtract 1 minus 1 is 0. What about this one? Step 1 says multiply the coefficient by the exponent. Okay, my exponent is actually 0, so 0 times 2 is 0, which means that there might be a 0 on here, but we don't normally say it. So we call this the algorithm, and this is a way for us to, given a position function, to get to a velocity function.